Hi everyone. Welcome to this M2D2 talk. Today we're gonna be talking about molecular representation learning from a perspective of topology, geometric, and textual description. Our speaker is Chengchao Liu, who is a fourth-year PhD student at Mila and University of Montreal. His research interests lie into representation learning, geometric learning, self-supervised learning, multitask learning, deep generative modeling, and geo discovery as well. To better know his work, the link to his website is on our website, so please make sure to visit his webpage. Thank you so much again for attending this talk, and thank you, Chen Hao, for for giving it today. Without further ado, we can start.
Thanks, Prudencio, for the introduction. Actually, we have been discussing about this to give this talk for 1 year, and yeah, finally, like today we can make it. And okay, so maybe let's get started. So firstly, let's take a review on the data structure and the representation of the molecule. And this is also like the one reason I started to explore this, because molecules has many modalities, and each of them can give us like different knowledge, and how to combine them to make the drug discovery into a real application is very fascinating. So of course, like the molecules are by nature the 3D molecular graph, or like what people call the conformation. And for the representation, people have been discussing using the equivariance or invariant graph neural network to represent it. And 2D molecular graph is perhaps one of the most widely used data structure in the drug discovery right now. And there are like hundreds of graph neural networks have been proposed to encode it, including like I think the latest one is a graph GPS by the Valency and Mila. And there are also like two more like old-fashioned ways for the data structure. The first one is a string, like either smile string or selfies, where we just write down the chemical formula using some heuristics. And typical methods include like the convolutional neural network, recurrent neural network, or even like the large language model. The last one is a fingerprint. And so the high-level idea is like we use some hashing method to encode the molecular graph into a big vector. And this is very old-fashioned way. And people have been just using the random forest or XGBoost for representation. And in addition to these four, recently people have been also trying to like encode the molecule in this biological knowledge graph. And this biological knowledge graph is a heterogeneous graph, which means like each node in this graph can be either like a drug, a disease, a protein, a genome, or etc. And this heterogeneous graph can be very large, and there are some very interesting like interactions or relations can be revealed from this graph. So, and the last one is a textual description. So as we may know, like there are many papers published in the chemical and or biomedical domain each year, and we can extract like the textual descriptions from this literature, and they can also provide us with some like functional, very high-level ideas of the molecules. So personally, I would say like I would separate these 6 modalities into 2 main categories. On the left is internal structure, or like the chemical structure of the molecule itself. And on the right is external knowledge. And I think there are some work starting to bridging the gap between these 2 modalities. I mean, the internal structure and the external knowledge. And in today's talk, so I'll be, of course, like I will be mainly focusing on the 2D molecular graph, which is one of the most widely used representation method. And first, I will introduce like how can we utilize the geometric information or conformation information to help with 2D molecular graph representation. And the next project we'll be discussing is how to do the pre-training on the conformation on the geometry information itself. And the last but not least is, as we just mentioned, we'll try to discuss like how can we bridge the gap between the two big modalities, I mean the chemical structure and the textual description. And so I will so my talk will be following these three pipelines. And if you have any question, feel free to stop me after the paper, each of the paper. Okay, so the first paper I want to discuss is GraphMVP. It's trying to learn or bridge the modalities of the molecules 2D and 3D information. So the ultimate goal is trying to make some molecular property prediction on the downstream tasks. And recall, like in the MoleculeNet, which is most widely used 2D topology target prediction tasks, like they only include the 2D topology. But also recently, like the community has put more efforts trying to gather in the large scale 3D geometric data set, for example, the genome. And then our question is like, can we utilize such 3D information to help augment the 2D representation? And so this motivates us to the GraphMVP. So we start with a mathematical framework. Basically, we are trying to maximize the mutual information between the two views, the 2D graph and 3D graph. The X is a 2D, hence Y is 3D. So mutual information has been widely used in the self-supervised literature. The high-level idea is like, okay, the mutual information measures the nonlinear dependence between variables. So once we can maximize such information, that means like we can learn representations that can, to the most extent, capture the critical information from the other view. And in our case, it's like we want to make the 2D representations that can, to the best, capture the 3D information, or vice versa. And in GraphMVP, following this, like the mutual information pipeline, we propose equivalent formulation, which is the summation of two conditional log likelihood terms, like the one I show here. So it's simply just like the py given x and px given y, which is how to generate the 2D from 3D and generate 3D from 2D graph. Then to solve this, we consider two big pipelines. The first one is we use an energy-based model to model this conditional log likelihood terms. And then we can use a very standard, like the noise contrastive estimation to solve it. There are a lot of mathematical details in the paper, but the high-level idea is like, we make this conditional density estimation into a classification problem. And the classification means like, if the pair of the 2D and 3D graph are for the same molecule, like the one I showed here, the X and Y, they are positive. And otherwise, like if the X and Y, they are referring to different molecules, then it's a negative pairs. And we just make this as a binary binary classification problem. If you're familiar with InfoNC or other like contrastive learning method, the main difference is like they just formulate this in the multi-class classification problem. Otherwise, they are pretty much the same. And we also have some interesting observation is like maybe for the graph level data, the EBNC or this binary classification problem can get like slightly better performance. But essentially, they are doing the same thing, which is contrasting the negative pairs and aligning the positive pairs. And the next task the next solution we consider here is a variational representation reconstruction. And so again, like we start with log likelihood terms listed above, and we propose a variational or evidence law bound to solve it. So typically, we can think of this as a VAE. So typically, the pipeline is like this. We have the 2D molecular graph, okay? And then we have this 2D representation after reparameterization. And then we want to do the reconstruction on the Y. But this is on the Y space, which is highly structured because it's a 3D conformation. And in the GraphMVP, we propose a proxy loss, which is like, let's try to do the reconstruction on the representation space instead. Okay. And if you are familiar with non-contrastive SSL literature, this can be reduced to the BYOL and simple semis. Okay. Yeah, and we also have like a follow-up work along this research line. which is like, let's try to do the reconstruction on the data space directly instead of the representation space. And this is still like in submission work, and I'm happy to discuss after it is public. So like people may ask why we didn't, because in the GraphMVP pre-training, we also have the 3D pre-trained representation. And people may ask like, okay, why we didn't try the 3D downstream tasks? The reason is because of the data size. For example, the one we use here is a genome, which has like 250K like 2D and 3D pairs. But for the downstream tasks, especially like the QM9, MD17, these are like very famous like 3D molecular data set for the property prediction. And their data set size, the difference on the size is very small. But after the submission of the GraphMVP, the good thing is like the community keeps like whole community keeps like adding more like, or extracting more data set on the 3D conformation, like the two are listed here. So this motivates us to step back to think like, okay, if we can do some 3D pre-training to reveal like more what is more like expressive geometric pre-training method. Okay. And this will goes to our next paper, which is the GeoSSL. And any questions so far on the GraphMVP? I'm happy to answer your question. No, then maybe we can go to the next paper. Okay, so the GeoSSL, like in this paper, we'll be mainly discussing like everything under the pure 3D setting, which means like in the pre-training, we only have the 3D conformation. And for the downstream, we also have only consider 3D conformation. So this is a very pure setting. And there's one key notion that we cannot avoid when we discuss about the conformation, that is energy. And which means like the molecule on the 3D space or on the conformation, it's not, it cannot be like arbitrarily distributed, but instead it is constrained by energy. And so the flow of this molecule on the 3D space can be formulated as a potential energy surface. The one I showed here is only 2D, only for the 1D line, but indeed it should be a 3D space. And so the data sets that's provided to us often like they only provide the original geometry, which should be the conformation in the local minima, or like with a most stable conformation. But in this work, we also provide some like very interesting toy example. And specifically is like we try to corrupt both the atom type and atom coordinate or atom position on the on these data set and see which one may affect the performance more. And the conclusion is like the coordinate is very important. And I think the DeepMind also has a paper, recent paper on this, which shows like the coordinate the coordinate corruption can be used as a data augmentation method. But we need to be careful about the noise scale that we added to this data set. Okay, so motivated by this is like, so the coordinate perturbation is important. So this motivates us to use this as a data augmentation method. And like the figure showed here, originally like the data set provide us with a G1 conformation. And we want to add a very small noise to get a G2 conformation. This can also be explained in two ways from the first one is from the like systematical design, which means like in the physical experiment, the systematic or the statistical errors cannot be avoided. And when we add this small noise from G1 to G2, it actually captures this kind of noise that cannot be avoided. And the second one is like, even though this kind of noise can be avoided, the molecules on the in the local minima is not static. It still has some very minor vibration. So once we are adding this very small noise, it's kind of trying to simulate this kind of vibration. So, okay, so now we have like the G1 and G2, these two like views, or the like the perturbed and original geometry. Then we follow the same pipeline. which is trying to maximize your mutual information. And we formulate this as a summation of two log likelihood terms. The idea is very simple. It's like just G1 given G2 and G2 given G1. It's like we just need to do this coordinate denoising. But there's one issue here. So the coordinate itself is essentially a type 1 feature, which means it has the same like the rotation frequency when we rotate the molecule. So when we design this kind of denoising, the denoising model need to be SE3 equivalent. And also like we may have some other technical like challenges, like we need to make sure after denoising they are in the same basis, and we need to do the basis matching. So this sounds a little bit, I would say like a little bit challenging. And we also have a follow-up work on this. But as a first step in the GeoSSL, we propose a an equivalent solution to this. That is doing transform this coordinate denoising into the distance denoising. So there are three steps. The first one is like, for example, from G1 to G2, we extract the pairwise distance from the G1, which is the D1. The second step is like we add a noise to each pairwise distance to get the D1 tilde. The last step is like with the D1 tilde and G2, we do the denoising back to D1. And we show in the paper like this kind of distance denoising is equivalent to the coordinate denoising as shown above. Okay, so this is for our GeoSSL paper, and if anyone has any question, I'm happy to answer right now. Yes, go ahead.
Yes. So one thing that I was wondering is what's the amplitude of the noise that you add to the molecule in the first place?
Oh, that's a good question. We didn't tune this very heavily, so I think we're just using the standard Gaussian scaled by 0.3, and these numbers are referred from the DeepMind's paper where they use perturbation as a data augmentation method. Yeah, but I'm pretty sure like there are more fancy ways to do this kind of adding noise operation. Yeah.
And do you add that noise to all the atoms in the system?
Yes.
Or just a few?
Yeah, I think we try both, like either adding noise to this coordinate or adding noise to the distance. Yeah, but the difference is very small. Yeah.
Yeah, so what I mean is not so much where you add the noise, but do you add it to all the atoms at the same time, or just a few atoms? Because if you add to all the atoms at the same time, that might change. So if you go back to the two previous slides, can you go back? Yeah, no, this one. Yeah, this one. So if you add noise, but let's say to all the atom, you can jump off, like you can quit this local minima, right? Yes. Depending on the amount of noise. So I'm just asking if you have any mechanism to make sure that you didn't kind of leave this local minima right there.
Yeah. This is actually one thing we have been thinking about, because like right now we don't have the data, so which means like the for example the MoleculeSTM they only provide the G1. So we do add some noise, and we are also worried like, okay, what if this jump out of this local minimum to another region? It's possible, but till now like we haven't got the data or like the oracles to explore this. Yeah, and by the way, I think the data set is also like one biggest limitation in this field. Because we need, for example, if we want to do some MD related simulation, which is highly related to this 3D pretraining, we do need those information. But yeah, I think right now we don't have those yet. But I know Joshua has a group working on this, so I'm also asking them if they can provide more information on this. Thanks.
Okay, perfect. Thank you.
Yeah. Thanks. And the next one. Yeah, I think we can go ahead. Clemens.
I think there's one question by Izzat and another one by Sami. Izzat, go ahead.
Yeah. Thanks a lot for the great talk. It was really good to hear. Just to see if I understand the idea of coordinate perturbation correctly, right? The idea is you perturb the coordinates to learn like an approximate coordinate invariance, right? So you get the same QM properties irrespective of where around that local minima you are, correct?
Yes, that's the expectation. Yes.
Okay, and then so then this entire approach would only be usable if you were interested in local minima, correct? So if you ever wanted to apply this to, say, transition states or something that's not a local minima, there, of course, you actually want to see different outputs from your network as you move around even a little bit on the potential energy surface, right?
Yeah, I think that this is definitely related. It's like how we model this, like during the pretraining, how we do this perturbation. It should be related to what kind of downstream tasks we are interested in. Yes.
Yeah.
Yeah. So far, like in this, because I think in this paper, the high level idea is like we want to provide a very general framework. It's like, okay, this may work, and if we have some very specific downstream tasks, of course, we need to do some very careful tuning on that.
Yeah. That makes sense. And of course, sure, the conformers, the local energy minima are usually the ones that are most important. Makes sense. Nice. Thanks.
Thanks. Any more questions? I think the next one is Sami.
Yes. Thank you. Interesting presentation. I want to know, is there any benchmarks, like kind of standard benchmarks to compare the different approaches? I mean, yes, that's my first question. And the second thing also, in the articles, you covered many aspects, but did you talk about like the molecular dynamics, or I mean, I think it's kind of important, the molecular dynamics simulations. Thank you.
Yeah, thanks. So for the benchmark, yes, we do provide that. Actually, in our paper, I think because there are like some parallel works, I think you may also be aware of. And in our paper, we provide like 9 baselines on the pure 3D pretraining. And we also prove that we also provide some qualitative results. And to your second question, yes, I think MD is a very good way to continue working along this research line. Just like right now, I think the biggest bottleneck is like the data set. It's like if we can have the whole MD or like some trajectory data set, then we can tell like what kind of, just as Procedure asks, it's like what kind of perturbation or what kind of noise added is reasonable. And what if like we add some very bad noise? Well, how will that affect the downstream performance? Yeah, I think that's interesting. Just we hope we can have the data set or have access to those trajectories to make this more interesting. Yeah. Thanks.
Okay, thank you.
Thanks. And, question? If no, then maybe we can move to the next one.
I think there's no more questions, so we can move on.
For sure, thanks. Okay, so the last but not least project I'm going to discuss is the MoleculeSTM. This is done during my research intern at NVIDIA with Anima. And so the whole level idea is like, as we mentioned in the very first slide, there are 2 big modalities of chemicals, of the molecules. The first one is a chemical structure, and second one is a domain text or textual descriptions. These 2 modalities are actually complementary to each other because, like, for example, one may just discuss about the chemical structure is only about the molecule itself, but the textual description can be very high level or like some very functional properties of the molecules. And so when we try to align these 2 modalities, we also want to reveal like 2 attributes of the natural language. The first one is open vocabulary, and second one is the compositionality. I will go into details like how we achieve this later. So the very first, so we just adopt very simple way to align these modalities, which is a contrastive pretraining, as we showed here. And specifically for the dataset, we create our own dataset, which is called PubChem-Click or PubChem-STM. It has originally, like PubChem has about 100 million molecules information. And but only like 280K has both like the chemical structure and the textual description. And we extract these for our pre-training. And below, I also show some examples with a smile string and also the textual description. Then it's like how we do this contrastive pre-training. Recall like the inputs are like pairs of chemical structure and textual description. Okay, like here I show two pairs. On the left is aspirin, and on the right is a penicillin. And then we do the encoding to get the corresponding representation. It's like two representation pairs. And then we just say like, okay, these two representation pairs are positive pairs because each of them correspond to the same molecule. Okay, and we will try to align these two representations respectively, or like just increase their similarities. But at the same time, we'll also do this contrasting, which is like, for example, the aspirin's chemical structure need to be dissimilar to the textual description of penicillin. Okay, and this is essentially the high-level idea of contrastive pre-training. It's like doing the contrast. We need to define the positive pairs and negative pairs, and then doing this aligning and contrasting simultaneously. Okay, so once we have this contrastive pre-training, we actually align these two modalities. Then the next step is like, how can we design the downstream tasks to reveal the fundamental or versatile usage of this model? The first downstream task we consider is a structured text retrieval. The example I show here is like, on the left, we have a chemical structure. And on the right, we have like 3 text prompts. We want, based on the MoleculeSTM embedding, we can get the representation for each of them. And then because they are on the same representation space, we can calculate the similarity. And we want to know if the actual pair has the highest similarity among these. So which becomes a very simple like T choose one optional multiple choice problem. Okay, so specifically for the downstream tasks, we extract like 3 sub data sets from the drug bank. And as you can see here, it's like there are many fields in the drug bank dataset, and we use a description, the pharmacodynamics, and ATC, which is short for this annotated therapeutic chemical code. You can think of this as a symptom description on the symptom of the disease. Specifically for this ATC, we think this can be somehow to mimic this drug repurposing usage, which is like given we want to know like existing chemical, what's the similarity between this chemical and all those unseen ATC code. So this is the first downstream task. The second downstream task is a text-based molecule editing, and which is also known as a molecule optimization, or the lead optimization. First, we need a pre-trained generative model, and then we will use this pre-trained generative model to learn alignment between the generative model and the MoleculeSTM. Okay. And here are some more details. So for this molecule editing, we actually have 2 steps. The first one is the space alignment. Suppose we have a molecule, and for each of the, then we have like the 2 models here. The first one is a deep generative model marked on the left, and the second one is a MoleculeSTM on the right. And we can get their representation following by like those pre-trained checkpoints. Then we just need to align these 2 spaces using a very simple like alignment module. In this paper, we just consider a Gaussian distribution to model this, which can be simplified as an MLP. And in some recent work, like the DALI 2, they also try some latent diffusion model to do this. I think that's also doable, but that's also worth exploring in the future. Okay. And then the second step is latent optimization, which is also the editing step. So the input of this step is like a pair of the chemical structure and textual description. And this text description often depicts like the properties that we desire what we expect the molecule to have. Then again, like we follow this these representation steps to get the representations respectively. The next step is like we directly learn or optimize the latent code. And this latent code need to be close to both representation using some like cosine similarity or AR2 distance. And once we learn this latent code, we can just do the decoding to get this output molecule. And we expect this molecule can be both similar to the input molecule and also close to the text prompt revealed on the right above here. And for this page, does anyone have any question? I can stop here for a moment.
Yes. I do have a question about the alignment phase. Because I don't see the decoder here, I'm wondering what's the mechanism you use to make sure that the alignment is correct.
So in the step one, there is no decoding part, just a representation. Because the decoder that we use here, it's fixed decoder, so everything is fixed. The learnable parameters in this on these two pages are marked in the pink. Okay, and so that means like the decoder is a fixed decoder, and here we are just using the fixed encoding on the very left arrow here.
Okay.
And then the point is like we want to align these two representation space.
Yeah. So the reason why I'm asking about the decoder is, let's say like I'm more or less sure that it's not 100%. There might be some small error, right, in the alignment. The alignment might not be perfect, but then let's say like the alignment is not perfect, and then you decode and you have another molecule. Right, because like, so that's why I'm asking the question. Please go ahead.
I think this is also like one potential error in this whole pipeline. Actually, during our experiment, we found like the decoding, the deep generative model itself has also some big issues. So, by the way, the one we use here is a MegaMoBART. That's a product by NVIDIA. And we think this part may reveal the most errors in the whole pipeline. For the alignment, in my follow-up project, I do try two different alignments. The first one is just using the Gaussian, and second one using the diffusion model. And the takeaway is like I didn't see too much big difference between these two. And I also asked some like domain experts. They are telling me like, okay, if you have very large data set to learn this alignment, I mean the step one, by expectation, like this alignment can be learned quite well. And also like for representation, yeah, one thing I forgot to mention is like for the representation, what's more important is the angle. So which means like the alignment here would be better using some normalization. So for example, a cosine similarity instead of the AR2. Yeah. And yes, I think that's pretty much the so for the alignment, I think there are a lot of work that can be done here. Yeah, thanks for mentioning this. Yeah, in the second step, as you can see, the blue marked angles, rectangles here, it's so it's like when we learn this when we learn this latent code, it's on this representation space of the deep generative model. So I think this may also like alleviate this misalignment issue a little bit, because everything that we care about is on the deep generative model latent representation space. Yeah. Thanks. Yeah, this is a good question.
Okay, thank you. Samir has a question. Please go ahead, Samir.
Do you hear me? Do you hear me?
Yes.
Yes.
Yes. Okay, that's very interesting to use the zero-shot approach for editing new molecules. The thing is that what kind of control we have I mean, to generate this molecule? I mean, can we exactly control exactly the structure that we're gonna generate? And also, is it possible to generalize to other chemical contexts? Because chemistry can vary, can change from a place from an organ to another, from a body to another. Is it possible to generalize to other chemical contexts?
Yes.
Yeah. So that's my two questions. Or maybe also, how is it possible to predict the properties? Because there is in biology there is emergence law, which I mean, whenever you have a new adjustment, you have new properties. So is it possible to predict the properties of the new generated molecules? Thank you very much.
Yeah, thanks for the question. And so for the first question, actually we do think about this, like what are the doable things using the MoleculeSTM? And like on my side, we also have this discussion in the appendix. It's like we separate this molecule editing task into two types. The first one is like the exact matching, and the second one is like fuzzy matching. So the point is, like, when we want to do this, exact editing. So when we do this exact editing, it's like, for example, we want to add some scaffold to the first or fifth carbon in this molecule. I think that's very hard to achieve for now, but it could be desirable in the future. And meanwhile, like from the domain experts, they have the vision, like, if we want to do this, we can just do this manually. It's like in the farm, which means like in the farm companies, they may not need this kind of exact editing like tasks that much. But instead, like what they may expect more is fuzzy matching. For example, it's like the example we showed here is a high permeability, or like other examples I will show in the next slide is like with more like the binding affinity score, or with lower binding affinity score, or like with higher solubility, with more donor acceptor, etc. I think these are like something that can be more like applicable for this MoleculeSTM pipeline in terms of the editing. And other chemical structures, yes, we will show this in the next slide. And the property about how to, yes, we do have some results on these edited molecule in terms of the property, also in the next slide. And I want to mention is like, in terms of this editing task, we found the evaluation is kind of the bottleneck. It's like, how can we do this exact evaluation on this edited or the output molecule? And so far, it's like we are only doing some very simple way. It's like the number of donor acceptors, this kind of evaluation matrix, where we can do the exact counting. But for more like challenging tasks, existing methods like in the machine learning community is to train like the pre-trained classifier to do this. But of course, they may have some errors, and we don't trust that yet. So that might be the next thing we need to we want to explore. It's like, how can we get more evaluation, more like trustworthy evaluation matrix, and how can we use those to help us to design or like to propose new editing tasks? Yeah,
that's very interesting. Thank you very much for your answer. That's very interesting. Thank you very much.
Thanks. And any more questions?
Roman, please go ahead.
Hi, thank you very much. Thanks a lot for the talk and the paper. Super interesting. You mentioned at the very beginning that the work demonstrated, if I heard you correctly, two key properties in natural language, which are open vocabulary and compositionality. And I was curious to hear you more about this and what you meant by it. Thank you.
Sure. Thanks. Actually, it's also in the next slide. So the high level idea, the high level idea is like, as you can see, the text prompt can be very free, which means like it can be any kind of textual descriptions. For example, like I want a molecule that can cure for example, the COVID-19. It may be happen next year, but we don't know. Like we can generate the molecules like that can. In terms of this text prompt, but the main bottleneck is again like the evaluation matrix. So in the next slide, we will show like how can we use a free open vocabulary to make different kinds of text prompt. Just one thing I want to highlight again is like even though we have those open vocabulary for the text prompt, we cannot verify them because of the limitation on the evaluation matrix. Okay. So yeah, finally we go to this slide. So here I show some very specific examples on the molecule editing, and I separate into 3 blocks. For each pair I showed here is like the input and output molecules are like marked, the changed regions are marked in the pink and blue respectively. So the first 6 examples I showed here are the single objective molecule editing. And as you can see, these 6 blocks are like the soluble, insoluble, high permeability, low permeability, more hydrogen bond acceptor, or donors. Okay. And these can be evaluated using the RTKit tools. And but also, I also want to mention, like for example, for the solubility or insoluble, the evaluation matrix is not that exact. Just right now we are kind of using a proxy tuples. Yeah. And the next one is about the compositionality, which means like for this text prompt, we actually combine 2 properties simultaneously. I think the one I showed here is a soluble and low permeability, and also like the soluble and high permeability. This is part where we mean the compositionality of the natural language. So typically, like when we do when we want to do this molecule editing in the molecule space, that means like we may need a lot of constraint to do that. But once we have the natural language or the textual description, the good thing is like we can transform this, transform the compositionality on the molecule data into this composition question on the natural language, which can be done quite easily because sometimes we can just use an add and add those 2 sentences or text prompts together. Okay. And the last 2 blocks the last 2 examples I showed are something very interesting from the domain perspective. So when the pharmaceutical company release their patent data, they are not just releasing the target drug, okay? They are also releasing some like intermediate drugs. Like we can think of this as a trajectory of the evolution of the drugs. And what we did here is like we put in some like intermediate drugs and add some text prompt. For example, the one I showed here is so for this input molecule, the text prompt is like, let's try to make this molecule with high bioavailability, and then it can generate these like the actual useful like patented drug in the database. Okay. So in this way, of course, like this is still very primary result, but we do believe like this kind of editing do show us some promising, like okay, we may in the future we can apply this in the more like realistic like domains or applications. Okay. And one more example on the molecule editing. So this is about ligand target binding assay, and the text prompt is from the Campbell dataset, and in this case it's a little bit long. It's like 2 sentences. Okay, and we show 2 examples here. The input molecule with a docking score. Okay. And once we do the editing, and the text prompt is from this Campbell dataset as shown here, the output molecules has even lower docking score. And we also show some demos. It's like it does have more binding sites or like lower like docking scores. Which again, like this is also under this 0 shot setting. Okay. Questions so far? Okay, so so far we have been discussing about the text-based molecule editing, and the last task is a molecular property prediction. It's the same as a GraphMVP on like those 2D molecular graph property prediction, and this is more like a proof of concept. So I won't go into more details, but you can feel free to check the papers. Please. Any question?
Yeah, sorry, I want to come back to the previous slide. I was still thinking about it. Here, like the model just generated the smile of the molecule, right? Not the actual 3D pose, right?
So what do you mean by actual?
So what's the output of the model? Is it the figure that you are showing, or is it just the molecule?
sorry.
Because it was a bit confusing.
Yeah, sorry. So for the editing, I only consider small molecule here. The pocket is only for the visualization.
Okay, so you just kind of, and how do you encode the protein in the
for the molecule editing, it's structure unaware. So which means like when we do the editing, we have no idea of what the protein structure should look like.
okay,
We only
okay,
have the text description as shown above.
okay, just the text description of the molecule, and you say I want a better docking score.
Yes.
Okay. Okay. Then how do you evaluate if this is successful? By just docking to a particular protein? Because
Yeah,
the
so
same molecule can bind to different protein, right? So
yes. So I think in the paper we pick up 6 Campbell datasets, and each of these 6 Campbell tasks, and each task has a specific target protein, and we just do the and for visualization we just pick like one most reasonable task for visualization. In the paper for evaluation, we kind of train like a classifier on those Campbell datasets because they have some Oracle like dataset. It's like positive and negative. Each of them is a binary classification. And then we use this pre-trained classifier as an evaluation to evaluate the effectiveness of the MoleculeSTM and other other baselines.
okay.
But for the visualization, yeah. Yes, go ahead.
So if I understand correctly, at training you have seen some molecule that bind to that target, and at testing you kind of give a new molecule and you want to improve the docking.
It's a zero-shot setting, so actually we are unaware of like what kind of downstream task we are going to use. And for the training here, specifically in the MoleculeSTM in the training step, the step 1 I showed in the 2 slides before, we are using the Campbell dataset. I think either Campbell or zinc. It's a zinc dataset. Okay. It's like only the chemical structure is utilized, and then for the editing we use MoleculeSTM. We're only like the smiles or the molecular graph and the textual descriptions are used. During this whole process, like there is no information about the protein structure. There could be some information about the protein information, like the one showed in this text prompt. This may include some information, but that's the only information available for the protein.
Okay, I see. Yeah. So the basically the information you need is encoded in the description of the task.
Yes.
Okay.
Yeah. We only have the protein information during the evaluation and the visualization. Thanks.
Okay, perfect. Thank you.
Any more question? Okay, so just another thing to mention is like we have a follow-up of the MoleculeSTM, which is trying to bridge the gap between the protein sequence and natural language. And this work is archived now and still in submission. Okay, so here's a recap. In today's talk so far, I've been mainly discussing like these 4 modalities of the molecule. And but I also want to mention like we have more works along the whole research line. For example, I have a molecular editing. It's a pure unsupervised editing method on the molecular ground. And as just mentioned, we have a protein design with a text model. It's also a foundation model, but the difference is on the protein sequence instead of the molecular ground. And for the 3D geometry, we have a geometric benchmark is still ongoing. And as mentioned above, like previously, it's like the molecule also has some biological knowledge graph, and we also utilize this to help us with like the molecule property prediction in the format of the multitask learning. And I think this is by far the very high-level idea of what my research and also our group have been working for the past 2 years. And for listening and any more questions, I'm happy to answer.
Thank you so much, Enha, for the great talk. If there's any question, please raise your hand and come off mute and to ask. I can kick off things. So the last paper is indeed very interesting, and I think is very promising. I'm just wondering, what's the next step now that you see should be taken to make this more, I won't say useful, but more practical in some sense?
Sure. Thanks. That's also one question we have been asking ourselves. So I think in terms of some methodology, because we are basically just following like the contrastive pre-training pipeline. So there could be some rooms for improvement for the editing task. But I think the main bottleneck for this whole pipeline is a data set. As you can see right now, we have like only 30K like molecule and text pairs. And we are expecting like we are expecting to generate much larger data set from the larger like domain, and this may need help from both like the machine learning and computational chemistry and computational biology experts. And I'm trying to find collaborations on this, and also discussing with Anima how to extend this. Yeah, and I think I think the next step is another like challenge here is like how to apply this for the real tasks. So for this project, we have been working for like 9 months, and 6 months we are trying to discuss like what are the useful or what are the reasonable downstream tasks that we can test. So this is a little bit interesting like process. It's like it keeps us rethinking like what the availability or like what's the accessibility of a MoleculeSTM, and how can we make this into the real impacts for the whole community. So in short, it's like we are trying. I think it's very interesting to discuss with different domain experts to see what are the interesting or important downstream tasks. Like for example, the editing or the lead optimization tasks we consider are very simple, just permeability, solubility, etc. But I'm pretty sure like the domain expert may have more expected properties, but that may be very specific for their own like research lens. So we are also trying to ask around to find those interesting tasks as well. Yeah, thanks.
Perfect. Thank you, Sami.
Yeah, sorry, just small comment. This was an interesting question. The next step, because I have studied pharmacology in the past, and I think the most important is what is the objectives. Is it do you want to optimize the properties of an already existing drug, or do you want to create new molecules for a new specific function or disease, or do you want to study the structure and function of a biological molecule? So it really depends on the objectives that the research group might have. But the methodology is here. But after that, yeah, it was just a comment. Thank you very much. Thank you.
Yeah, thanks. Yeah, this is actually also the goal why we propose MoleculeSTM, because I think this is a very big research line, and this can something also like bridges conformation into this whole like even like for example the docking experiment can also be applied in this case. Just we may need some textual description and training data, and also like as Sami mentioned, it's like we are also interested in like how to explore this to the new disease, to cure the new disease, or like how to combine this with a protein or genomics data, etc. Thanks for the comment.